Extreme weather events can cause significant damage to power grids. Any operational framework aimed at improving the physical resilience of power grids must account for the distinct characteristics of various high-impact, low-frequency events. Recognizing these characteristics is crucial, as each extreme weather event exerts unique spatial and temporal effects on power system infrastructure. Among these natural disasters, wildfires stand out as one of the most dangerous high-impact, low-frequency events, posing a substantial risk to the reliability of power networks. To address this challenge, ICCS NTUA presents the Wildfire Events Simulator, a tool which can become a valuable asset for distribution system operators. The end users obtain a flexible tool able to model wildfire events, assess their spatial and temporal impact on distribution networks such as line outages and spatiotemporal load shedding, and determine an optimal event-informed scheduling strategy of the network resources to enhance its resilience and to mitigate the disruptive effects of wildfire events, thereby supporting DSOs' decisions. This assessment is based on the evaluation of the wildfire trajectory across the distribution network, considering both evolving weather conditions and the specific topology and characteristics of the analyzed power network. For this demonstration, we will utilize the 125-bus Greek pilot site network located in Xanthi to validate the practicality and application of the tool. The execution process will be logged and monitored through a console to keep the end user informed of progress in real time. The underlying architecture of this AC optimal power flow model follows a straightforward, sequential process. The first step involves gathering network data, which includes information about asset connections, distributed energy resources, technical and cost parameters, as well as weather-related parameters. These weather parameters are crucial for simulating the dynamic effects of wildfires. The tool requires forecasted hourly profiles and standard deviation for parameters such as wind speed and direction, load demand, ambient temperature, and solar radiation. Given the inherent uncertainty in weather parameters, a scenario generation and backward reduction module is employed. This module generates hourly profiles and uses Monte Carlo simulations along with probability distribution functions based on forecasted values and standard deviations. These scenarios are subsequently reduced to a manageable set, representing the most probable outcomes while maintaining the integrity of the stochastic information. This Monte Carlo-based approach allows the model to capture a broad range of possible scenarios, including worst-case conditions. To assess the spatial and temporal impact of the wildfire, the tool models the propagation of the wildfire across the distribution network. The dynamic line rating of overhead lines is incorporated to simulate the effects of the wildfire on conductor temperatures and flowing currents. This ensures the tool accurately reflects the evolving conditions during the progression of the wildfire. Once the scenarios are generated, the reduced set of scenarios is fed into the AC optimal power flow model, which is solved for each scenario, and the results are exported into an Excel output file. The tool provides for the DSO an event-informed optimal scheduling strategy of power resources to enhance the resilience of the grid and calculates the expected values, including the expected energy not supplied and associated costs over a 24-hour period. As can be seen, the model is solved successfully and results are exported in the output Excel file. At the conclusion of the tool's execution, the results are displayed through an intuitive Power BI online interface. By simply clicking the Run Flow button, the report is refreshed to depict the latest results. The report keeps the information of the latest date and time of tool execution. At first, the report is empty. When updated, it allows DSOs to view real-time updates on wildfire impact assessments, weather conditions, line failures, failure times, expected energy not supplied, and expected transactions with upstream system. For this demonstration, the threatened distribution line is assumed to be the one connecting the feeder to the upstream system. As weather conditions evolve, the distance between the wildfire front and the line decreases. Once the wildfire approaches, the conductor's heat gain rate rises sharply until the line is forced out of service. This occurs at different time steps across scenarios, depending on the specific weather conditions, leading to feeder isolation. The report shows outage times at the 17th hour in some scenarios and the 18th in others. The model then evaluates the expected power transactions with the upstream system up to the outage, along with the associated spatiotemporal load shedding and costs. The Power BI report also presents a detailed breakdown of network data, asset connections, and overall power consumption and generation scheduling, enabling DSOs to make informed decisions on optimizing grid operations during wildfire events. Specifically, by evaluating the outage time and resulting feeder isolation, the model schedules full battery charging when solar generation exceeds demand and activates the backup controllable generator once the grid is isolated. This ensures critical loads are supplied while minimizing non-critical load shedding. By integrating both conventional and smart technologies, the Wildfire Event Simulator is a valuable tool for enhancing the resilience and security of power systems. It supports DSOs in navigating the complexities of wildfire events, ultimately helping to safeguard critical services and enhance resilience.